Hello everyone, welcome to our class. Today we are going to talk about the data representation for floating point. So how to use binary to represent floating point is also really interesting topic for us to discuss. As we know, there's a impossible like a different combination of floating point we can have. You can have so many digits after decimal point. It can be 1 digit, 10 digit, even like infinite digit. So definitely, if we only use our memory, uh, the memory should be limited. We cannot use any of this memory to represent this floating point, right? So because of this, how to provide a reasonable algorithm or to provide a way to store this decimal point, like each digit in a decimal point inside a limited memory is really interesting topic. So today I'm going to show you how our like IEEE standard they defined in our system to support this kind of binary storage of the floating point number. Okay. Okay, so before we move to the floating point, this is the one sequence of byte. I use 4 digit binary. So every digit here are binary. So I use really small, simple binary numbers to represent integer. If it's an integer, you can see that for the integer, it can be 0000 to represent decimal number 0, right? It also can be 1111 to represent decimal point 15. So if we have a 4 digit of the binary, we can represent integer from 0 to 15, right? Okay, so now let's look at if we want to use the 4 digit, only 4 digit to represent floating point. How can we do? The first idea we can do is maybe we can split up. So we try to imagine one like a virtual decimal point in this case, and we use every number here to represent the decimal point, the number, the integer number before decimal point, and we use the rest of the digit to represent any numbers after the decimal point. So in this case, if we follow the same logic of the same algorithm we use for binary, this one can be 2, 0, this one can be 2, 1. This one, we use the reverse one, so it will be 2 minus 1 and 2 minus 2. Okay, so if we somehow understand this idea, what we can do here is that we can represent 0, 0, 0, 0. So it will be 14.0.0, right? We can also do 1, 1, 1, 1, which will be floating point 1 times 2, 0, 1 times 2, 1, so it becomes 3. 1 times 2 to power of minus 1. 1 times 2 to power of minus 2. In this case, it will be 0.5 and 0.25, right? So at the end, this part will be organized, will be 0.75. So it can represent 3.75 in this case. So if we just split up the digit, use part of digit to represent the integer part of this floating point number, another digit to represent the floating point part of this number, then we can easily use the limited memory to represent different data. So we can represent 3.25, we can represent 1.25, we can represent 1.5 in this case by using 4 digit. Okay, so this is the first idea we have. This is the first idea we have. However, you can also notice that if we use this approach, originally compared to the original data, if we use 1111 here, for integer, if it's for integer only, not floating point, it can represent 15, right? So this 15 compared to this number, it has a significant difference. So if you want to use part of a digit inside this binary number to represent floating point, means the maximum number you can represent, this 4 digit can represent, will be significant job. So basically, if original number is 15, the new maximum number will be almost like the square root of 15 because you lose like half digit. So let's look at the second approach. So for this approach, we can see that we will lose a lot of numbers we can represent because we lose a lot of bit to represent the floating point number. So even for the 4-bit, it's come from 15 to just about 4. However, you can imagine that when you have, let's say, a 32-bit at the end, originally 32-bit can be used to represent like a 2 power of 31 minus 1, which is almost 4 billion. 4 billions, the maximum number can be 4 billion something, right? So if you do the square root, basically it's become almost like 216 minus 1. It only can represent 65,000. So from 4 billion to 65,000, you can see it's definitely significant difference between the number you can represent without using floating point and the number you can represent after you reach floating point, right? So this is why we should come up with the second approach. The second approach here is that we still use the same idea. We start here. However, we don't treat this part as integer part of this floating point. We also do not just do the plus at the beginning. So if you put down here, you have integer plus a decimal point, means you got the final floating point number, right? So we use plus here. However, we don't need to use plus. We can somewhat consider a different possibility. So the idea here is that we still group these two together. We still group these two together. We got number A here, number B here. However, we don't use A plus B, but we use 2 power of A times B in this case. Okay, so 2 power of A times B. So let's see how this works. So assume we still have 0, 0, 0, 0 at the beginning. Then this number can represent is 2, 0 times what? 0, right? So it still gives you 0. Okay, so how about if we change the number to 1, 1, 1, 1? In this case, because 1 times this one is 2 power of 1, 2 power of 0, 2 power of minus 1, 2 power of minus 2. So 1 times 2 power of 2, 2. 1 times 2 power of 0, 1. So the first group is 3, right? So with 2 power of 3 times 1 and 1, it's give you 0.5 plus 0.25. At the end, it should be 0.37, 75. Okay, it should be 0.75. Okay, so if we use this number, 2 power of 3 will become A times 0.75. So result will be 6. So 6 is not that good compared to the original value, 15. So did you see that original value is 15? It does not compared to the 15 is not that good. However, it's definitely significant better than this number, 3.75, right? So if we follow this approach, we can definitely improve this a lot if we have enough bit to represent a floating point. So if we only have 4 digits, you cannot see that significant difference. However, when we have more bit to be here, imagine that this number can be really, really big. If you have a, let's say 16-bit, if you only have a 16-bit to represent here, it can be 216 minus 1, right? And you use this number as an exponential number. For 2 means you even improve this kind of big number you can have. So this kind of formula will become really, really powerful when you start to increase the number of bits you want to use to represent a binary. For a 4-bit, it can be not that good compared to others, but if we can increase the bit, it's even better. Okay. So now let's look at the third approach. For the third approach, we still follow the same thing. We do this group and this group, and we do 2 power of group A and times group B. Okay. So if we have this kind of group, the only difference here is that we can add one more one here. 1 plus b times 2 power of a. Okay, so what does this? If we trying to do this, a good thing here is that we can represent really close to the number we originally have. For example, if you have 1 here, follow this idea, it will be 2 power of 3 times 1.75. So this case will be a times 4, 7 become 14. So for this kind of algorithm, you can represent 14 as a maximum value for the 4-digit. Compared to the original data, 15, it's almost there. It's almost there, right? So just by magically plus 1, it can make the entirely algorithm similar to original one. Okay, so but you might ask a question: where do we represent this one in a memory? Inside memory, we have a 4-digit, right? Which bit we can use to represent one? Think about this. This one is a constant value. We never change it, right? So if we never change it, we don't need any memory space to store this one. We don't need to use any memory space to store this one because it's a constant value. So every time we got this digit bit out, we do the computation, we automatically plus 1 to the group B, then times 2 power of group A. This is the idea.
Oh, I have a question. In the final formula you provide, it seems like this is a very good formula. However, I also noticed the issue, which is that if all the digits are zero, the number it can represent is not zero because you is plus one in a big group, right? Can you tell me how to represent zero in this case?
This is excellent question, Snorlax. Okay, so let's see this example. So this is the idea. So the idea is we still group these two together. One called A, one called B. We still run 2 power of A times 1 plus B as the idea. Okay. However, we want to make a change. What's the change? The current A can only represent a number 0 or larger than 0. So which means these two power of par will always be a big number, big positive numbers. Okay, so the minimum number can only be 1. Okay. However, think about it. If we want to represent a lot of different kind of floating point, we should also consider a number can be really small, like 0.0000, a lot of 0, then maybe 1 at the end. So in this case, this kind of like a formula is definitely not working. But one trick we can apply here is that we can just make this number minus something. So when we minus something, this number cannot be guaranteed to be 0 or positive value. It can be a negative value. If 2 power of negative value means the number will become smaller and smaller and smaller. So 2 power of negative 1 will become 0.5. 2 power of negative 3 will become 0.125, right? So if we can consider a big enough negative value, eventually this number can close to 0 at the end. This is the idea. Okay, so let's just put one example. Even this shifting number, I just put 1, it can make a difference. How? So assume we have 0, 0, 0 here, right? A is 0, B is 0. So this 1 will become 2 power of 1 times 1. It's actually become 2.5. Compared to the original case, 1, 2.5 will be definitely close to the 0, right? This is the idea. Okay, so this is the example. Actually, if we have a 32-bit in our system, based on the current standard, what we usually do? We actually give 1 bit as a side bit, just like an integer, we want to provide side number, side integer. We also want to provide side floating point. So there's a side bit at the beginning, and then you can see there's a shifting here, right? So we try to use a bit to represent this exponential value, and the exponential value a bit can represent 0 to 255. So this is why we choose the offset minus 27 here to make sure it can represent a really small exponential number. And then we also have a 1 plus the second combination come from the rest of the 23 bits together. So if you understand the point here, what we have is this example. The first bit is 1, and then we have 1, 0, 0, 0, 0, 1, and then we have another number. It can represent a number like this. And when we compute it, you can see the exponential part of this number it will become 129 minus 127, so it's only become 2. And then we do minus 1 times 4 times the rest of the decimal number, floating point number, we got the final value. So this is the whole idea. We put whole idea together into the system. That's the reason we have a specific format for the exponential part, for the floating point part, and also for the side bit in this case. So this is for today's lecture. We introduce how to use binary to represent floating point numbers. So I step by step to introduce the key point of this kind of systems. Why we use exponential number, why we use exponential number minus some shift number. And we also mention what's the virtual one, not exist in any memory space. There's a virtual one be used to compute the final floating point number and why we need this virtual one. Okay, so hope you like this lecture. Hope you enjoy the class. Hope you can explore more in the computer world how to use binary, this kind of binary number to represent different stuff, different type, different object in the computer world. Okay, so hope you enjoy this class. See you next time. Binary representation of floating point is awesome.